Hello, everyone, and welcome to ISPE's April 1st Friday webinar, Recycled Plastics and Storm Drainage, presented by Bryan Miko. My name is Katie, and I will be your moderator today. The handouts for this presentation are available in the Handouts section of your webinar toolbar and on the website. The quiz can be found on the website. A direct link to both is included in your confirmation email. Be sure to complete your quiz by Wednesday to ensure timely delivery of your PDH certificate. All attendees have been muted to avoid audio feedback. If you have a question, please type your question in the question box and I will read it aloud at the end of the presentation. With that, I'll go ahead and hand it over to Bryan.
Okay, thank you, Katie, and thank you, ISPE, for giving me the opportunity to present this webinar today. The title, as Katie stated, is to talk about recycled plastics and HDPE. Recycled HDPE specifically for stormwater drainage. And I'd really like to start out the presentation a little bit talking about the reasons why this is important, why this is valuable to us as a country, as a state, and as a locality as well, and then talk a little bit more about the how and what behind why some of the changes are happening to national specifications and other things as well. So before really jumping into the nuts and bolts of talking about recycling plastics and stormwater drainage, I do like to start off with talking about the overall global view and picture of where we all stand from an infrastructure standpoint as a country, and what our job is as engineers to really help raise this grade that you see before you now on the screen. I think most folks are very aware of and are well versed in the ASCE's infrastructure report card that was put out in 2017, updated every 4 years or so, which resulted in a D+ and has not changed really very much over its last few report card segments sent out. The D+ grade in the ASCE report card refers to much more than just quality. The other aspect of the ASCE report card, which we can really weigh heavily on the report card grade itself, is the amount of available funding that can go towards our infrastructure as a nation. The $3.9 trillion that you see on the screen here is actually the amount that we stand to lose as a country if we do not invest in our infrastructure. There's a $2 trillion gap right now, as they've estimated. But if we don't invest, there's also a huge potential loss in our national productivity and our GDP. And really the mentality that we all need to have is that we have to start looking at the way that we do things differently. We have to look at ways to be more sustainable in the resources that we're using, and really leverage our knowledge and our engineering backgrounds to help close this gap and help our nation going forward in our state too. On really another side of things as well, there's a lot of reporting and discussions about what we do with our waste and what we do with our resources that are simply dumped or sent to a landfill or could be residing in other places on the globe and on this earth. And this photo is one of a few examples where there's actually aggregating piles and floating plastics and floating debris in our oceans. I think a lot of folks have heard a lot about this problem and this continued growing factor on our environment. I'm not going to dive too much into the details of that, but I think a lot of folks are aware of the fact that this is a growing problem from a waste management standpoint, and it's something that we certainly need to address. Additionally, with a lot of the changes recently to some of our foreign policy stances as a country, China is no longer taking a lot of this plastic waste and debris that they've been taking for quite a long time and using for their own operations as well. So not only is there an increased amount of plastic that's being thrown away as waste and being dumped in various places across the earth, but us as a country, we're also going to have a much larger task in dealing with some of this waste moving forward, considering that China has shut off a lot of that, the shipments of these bales over to their country for their own uses. So I just want to give a few facts and figures about what recycling plastics can mean to our country and to us as citizens of the U.S. Every time 1 ton of plastics is recycled, it equates to, I'm going to give a few different examples, but it equates to either energy savings or space savings. So for every 1 ton of plastics that are recycled, It saves about 5.7 kilowatt hours of power. It saves and reduces the amount of oil that needs to be extracted out of the ground by 685 gallons of crude oil. About 98 million BTUs of energy. And this is very important to note down and remember, about 30 cubic yards of space in a landfill. So from a spatial standpoint and from an energy and a power and a resource standpoint, recycling 1 ton of plastics can mean a whole lot to our country and our resulting infrastructure. So the question is, how can we take this commonly used product and turn it into something much more value? Most post-consumer products and post-consumer recycled plastic bottles are typically intended for service lives that are in the 6 months range. And are we able to take that type of product and turn it into something much more usable that can last for 75 or 100 years in the ground? And that's really the topic and the task that can bring a lot of value to us from a whole slew of applications, just kind of like I talked about previously in outlining the problem itself. So I do want to give some background into some of the history behind what's already been occurring from a recycling standpoint with taking recycled plastics and turning into a much more usable product. Green Line Polymers is a subsidiary of ADS, and last year we recycled 425 million pounds of plastic and utilized it into high-performing high-density polyethylene pipe. 425 million pounds is about 210,000 tons. So if you tie that back to kind of what we discussed further, for every ton you're saving 30 cubic yards of space in a landfill, multiply that by 210,000, and you get the amount of space that was effectively saved by recycling that 210,000 tons through this process. We do have the fortune of having 8 of our own recycling facilities, which enables us to really dig into the details of the recycling process, refine it, and you can see, as the chart in the bottom right kind of indicates, over the past 12, 13, 14 years, we've continued to refine that process to be more and more viable from a usability standpoint in a high quality performing pipe product as well. Currently, from a standard standpoint, ASTM F2648 is the standard that's out there for use in basically non-public or only in commercial or private development type land drainage applications. And those statistics that you see there are specifically for that pipe product alone and how much recycled content that we utilize, and have continued to increase the amount of recycled utilization over time. Again, as a more global overview of the recycling process, I think it's important to understand how all of these things arrive at our recycling facilities and how it turns eventually into a 75 or 100-year design service life type product. Obviously, the first place that the recycling place starts is at consumers' homes. They will typically separate out various types of materials, put them in a recycling bin. It gets taken away to a distribution facility that will actually sort and create different bales of different types of recycled content. And they'll typically just split it between plastics and paper and do more of a global sorting process. From those distribution facilities, we then pick them up there, or they get shipped to an actual recycling facility. I'm actually in Clarion, Pennsylvania right now at one of our 8 recycling facilities that recycles over 100 million pounds of high-density polyethylene on an annual basis. And they receive bales and segments of HDPE and recycled content from over 100 different facilities. So once it is received in that facility, it gets processed in a very long multi-stage process where we actually break down the bales. I'll go through some of these steps, and out will come basically either flake or pelletized recycled HDPE, that's very well washed and sorted and cleaned that can actually be then turned into and used in our extruders at pipe manufacturing plants and then returned to the marketplace. So I kind of mentioned some of the steps in the actual recycling facilities and plants themselves. I did want to highlight some of those global steps again. The first real step after you break down the bales and run them through some conveyors and vibrators to pull out the smaller portions and pieces is really hand sorting. You can see a good example of the lines right here, and I do want to humbly submit to everyone here that this is a very difficult job. Having been in the plant for the last couple of days, there's all sorts of smells and aromas that come from a lot of these bales that make this job. I just have so much respect for the work that they do, working here 9 hours a day, sorting through all this material, and really doing a great job of separating out the different types of plastics, the different types of contaminants that aren't HDPE, that aren't reusable in a pipe-like product material. So this is really the first step. They take all of the debris that we don't really want and they throw it in the middle trough, and that gets pulled away and taken elsewhere. And what's left is as well sorted by hand HDPE and plastics that we can utilize and recycle and grind up and put into pipe products. So from that hand sorting, I mentioned the grinding portion. That's really the next step. After it's hand sorted, it's all ground up into kind of a combined mush and a flake type material like you see right here. After the grinding process, it's typically run through several wash baths. This is the most critical and important step to the recycling process, and is one of the only ways that you can truly separate out plastics and materials that are lighter in density than water from others that will sink, like metals and woods and things like that. We do utilize some conveyors of magnets to pull out steel and iron and other things, but the wash baths are extremely critical to separating out plastics from just about everything else. After the wash bath happens, they'll actually compress them and squeeze out a bunch of moisture. They'll run them through a series of dryers and batches. And really, this is what the wash bath is trying to accomplish. It's trying to separate out things that are lighter than water, aka plastics, from things that are not. If we have a very good wash bath stream, we sample it on a very routine basis every shift. This is the type of content that we'll pull directly out of our wash bath, actually, just to test and see what kind of quality we're getting from a washing standpoint as well. The washing is the second bottleneck in the process. The drying process is actually the slowest portion of our manufacturing process in terms of recycling and grinding plastics. The drying itself is really important as well, because any moisture that's found in these flakes can really affect processing in an extruder or down the road in the actual manufacturing process itself. We do utilize some additional processes to continue to refine the thermoplastic after it's settled out and floated on top of the water and been removed and dried. The most difficult contaminants to remove out of the process is actually other thermoplastics, because they are also lighter than water in their weight. Polypropylene, for instance, is about 0.90 grams per cubic centimeter, and high density polyethylene is about 0.95 on average for density. So both of those will float on water, and that can lead towards needing some additional processes like this to pull out additional thermoplastics. So what you're seeing here on the screen is actually a pelletizing operation, where we basically melt and push the plastic through various meshes of screens. All thermoplastics melt and are molded at different temperatures. So it's geared towards melting the HDPE, pushing it through the screens, and catching a lot of that additional debris in these screens. After we've done that melting, we actually run it through a pelletizer as well. The pelletizing makes it really great for processing in our actual plants and extruders for manufacturing, but that's what a typical recycled pellet will look like, whether you buy it from an actual manufacturer or like us, we do it ourselves. from that pelletizing process or the flake process, that's where it really enters and gets brought back into our plants for manufacturing. So after that entire recycling process, we do a lot of quality checks on things like density, stress crack resistance, melt flow rate, moisture content, like I kind of mentioned. And we really try to get a good sense of what that recycled content is at from a performance level. When we go through those quality steps, they then get shipped to our plant, and it gets blended with a variety of different components. So you can kind of see here the typical components that are utilized in an extruded blend of recycled plastics for the pipe material itself. It'll include obviously the recycled flake or pellets. It'll include usually some portion of virgin pellets, and it will typically include a carbon black pellet or an antioxidant packaging that goes along and inside with the blend to make sure that you provide that antioxidant protection for long-term service life. One of the difficult things to quantify with recycled plastics is how much antioxidant packaging is left in the remainder of the post-consumer ground resin. So adding in that antioxidant packaging is critical towards long-term service life and performance. And that's what really reinvigorates and really juices the blend to be more applicable for long-term service life applications. So as those are all blended and then put into the hopper of the extruder, it gets melted, pushed through with an auger into the extruder and turned into pipe like you see here. Obviously, it can be modified from that point to be cut into various lengths of sticks of pipe, perforated for different applications, and you can apply things like gaskets and at the end of the line basically as well. So I hope that was a helpful step-by-step process for understanding how the recycled HDPE gets sorted, washed, cleaned, quality checked, mixed together in our plants, and then utilized to manufacture a high-performing product. But really the question that was put on the table about 11 years ago by NCHRP and a lot of the DOTs was, is utilizing recycled plastics going to present a problem from a service life standpoint, and how can we accurately quantify whether or not a 75 or 100-year service life is attainable for public applications? Like I kind of mentioned, the ASTM F2648 standard has been around for quite a long time and has been used in commercial and private development type applications, but to date there is no public use standard, be it AASHTO or ASTM. So this is really the question from a resiliency standpoint and a sustainability standpoint. It's great that recycled plastics are being utilized, but will it meet the demands and the needs of our infrastructure as well is the overarching question. So I mentioned NCHRP, and 11 years ago, they embarked on a journey to tackle this research project and tackle this question of, is that attainable and is it quantifiable? And they did so through a handful of projects. This is a list of the three that I'm going to talk about today, and the most critical ones. NCHRP Project 4-32 was about a $350,000 project that was completed in 2011 and formally published in NCHRP Report 696. That portion of the project is really geared around quantifying in a lab what kind of quality you're getting from a resin standpoint and how minimal your contamination is in that blended resin itself. The second step was to validate via field performance and field evaluation. Did the quality test that we created in NCHRP Project 4-32, is it translatable to the field? Is it verifiable with field data? Can we then take that quality test that is created and turn it into a translatable service life that's practical and real and consistent? And thirdly, there's some additional research that was done alongside the NCHRP project to evaluate live loading and fatiguing, and if utilizing recycled materials has any effect on HDPE's ability to perform in in live loading and fatigue type applications as well. So before diving into the nuts and bolts of the standard updates and the research behind it, I do want to kind of give a quick highlight of the research and what came out of it. Basically, the AASHTO M294 standard that's been used for quite a long time and has solely been with virgin HDPE resin will now include the ability for manufacturers to utilize recycled HDPE content. The requirements for that product, when you use recycled, must meet or exceed the current virgin resin requirements. And there's also a standard recommended practice for ensuring 75 or 100 year service life based on a lot of the additional quality tests that are required for recycled resins above and beyond what's required for virgin. So it truly is a performance-based specification that is geared towards providing a product that is as good, if not better, than what's currently being used from a virgin resin standpoint. So to understand what has been done in the research and why it's important and why that's translatable towards actual field performance, it's important to understand some of the basics around long-term failure modes for high-density polyethylene and, frankly, thermoplastics in general. This graph, if you ever dive into research on plastics and thermoplastics, is referenced quite a bit when analyzing the long-term failure mechanisms for thermoplastics. There's really three stages that are seen typically. Stage one is considered a ductile failure. A ductile failure is basically where you are exceeding the stress that is being placed on the plastic is exceeding the strain capacity of that plastic, forcing it to exceed the strain capacity of the plastic, and it ruptures or breaks and tears in a ductile manner. That stage is very appropriate, especially when you're looking at pressure pipe applications. A lot of the solid wall HDPE pipe that's designed for water main is designed to handle some of those very high internal pressures and stress levels that are placed on the pipe wall. And when they do the burst testing via ASTM standards, it's really geared towards understanding that first stage failure and making sure that you're designing it so that that stage one failure doesn't happen in the field. It's not as common for gravity flow applications, which is really what this research is geared around here today. The only place you may see the stage one ductile failures in a gravity flow application is if you have damage during construction, where it's run over with too little of cover, and the end user is placing high levels of stress on the pipe via construction loadings or handling, and you can see local tears or rips or ruptures through the pipe wall in those circumstances. From a long-term service life standpoint, however, obviously when it is being installed, that's why we have measures to make sure that's within an allowable deflection limit and it's in a serviceable state. If it's above and beyond that, it's typically due to construction damage and that type of issue. So this research is really focused on, if it is installed in a serviceable fashion, how can we guarantee that it's not going to see premature failure due to embrittlement, which is what stage two is, basically environmental stress crack resistance, or stage three failure, which is not having that antioxidant packaging in the plastics themselves. So really the interesting part of the research was, how do we evaluate that for recycled plastics? For virgin plastics and virgin resins, there's a test out there called the notched constant ligament stress test or strain test, NCLS test. And it's basically where they take a notch into the sample, they pre-crack the wishbone sample, and they pull on it for a period of time in an hydrogel bath to see how long it takes for that crack to propagate and pass through the entire sample. And that's really used as a control measure to make sure that the HDPE resins being used have enough stress crack resistance when placed in the field at higher levels of stress. The problem with the notched test is that it doesn't address the crack initiation phase of stress cracking. With recycled plastics, obviously the big concern is contamination still existing within the blend in the resin itself. So how can we adequately measure contamination and assure that even if there is contamination in the plastic, that it's not going to turn into a propagating crack that's going to lead to additional stress cracking and embrittlement and ultimately failure long term. And that's what the first NCHRP 4-32 research report was geared around, that resin testing piece and the predictive modeling aspect after that. So through the research report, there is a test now, an ASTM test F3181, that was developed specifically for testing and identifying that crack initiation through propagation phase of utilizing post-consumer recycled HDPE. Basically, they created very large wishbone samples. There's 3 test setups that are done, which we'll talk about a little bit, with 5 samples per run. And on the right side, you can actually see what when eventually the wishbone samples are pulled for a certain amount of time with a certain amount of loading, what a piece of contamination looks like in the recycled resin and how that starts a crack and how that propagates across the sample itself. The nice thing about thermoplastics is that you can actually have a very good sense of what it's going to act like 75, 100, 200 years from now through a variety of really 2 main methods for analyzing long-term performance. The poplar shift method and the rate process method have been used for a very long time, especially in the gas pipe industry, and the auto industry, and others, to really have a great understanding of what this viscoelastic thermoplastic material is going to act like down the road, given a certain level of stress. So both are very viable options. The methodology that was utilized and really validated the most through empirical data was the poplar shift method, which you'll see here in a second. So I mentioned 3 runs or 3 test conditions before. In the F3181 testing, basically those 5 samples are really 15 samples, but 5 per condition are tested at elevated temperatures and elevated stresses to accelerate the failure mode and to give us the ability to extrapolate that to a stress time curve, if you will, a log curve, to determine how long it's going to last given that stress level and condition. So the tests are done at 80 degrees Celsius, 70 degrees Celsius, 650 psi, and 450 psi in combinations to give you the 3 test conditions. So once you have those 3 test conditions, you use what's called a stress shift factor and a time shift factor to shift the data points to an ambient temperature or a representative temperature. In the research, they utilized 23 degrees Celsius, which is very conservative from the standpoint that the southern states like Florida or Texas will likely see ambient temperatures in the ground, soil temperatures in the ground closer to this 23 degrees Celsius mark. In a lot of the northern states, you'll obviously see, excuse me for going a little fast there, you'll see a lower ambient temperature just naturally because of us being in a northern latitude or far northern latitude. That's actually an excellent thing for the thermoplastics itself. Utilizing a higher design temperature for evaluating the service life of the pipe itself will actually yield a curve that is further down and to the left, so a lower stress level and a lower time frame to cause failure, basically. So this is what a typical master curve at 23 degrees Celsius would look like after running the UCLS test on a blended resin. You can see lower confidence and upper confidence limits established based on statistical analysis. And throughout the research and the reporting, the established design stress that's utilized in a lot of service life evaluations from states that utilize that, like Florida DOT or Pennsylvania DOT, is typically about 500 psi stress seen in the pipe wall itself, which is a conservative estimation based on what they've calculated in the actual pipe wall, usually around 350 to 375 psi, with a 50% safety factor added on top of that. So you can see here with this service life prediction illustration model, these UCLS tested resins at 500 psi would last 234 years before seeing any kind of stress cracking occurring in the pipe wall itself. So that's all well and good. I think we all know, though, that lab testing doesn't always translate to actual field performance. And the second phase of the research report itself was really geared around utilizing that test, the UCLS test, and seeing if we can validate its predictive modeling into actual field testing and field verification. This is a bit longer segment of the project. Obviously, real world and full scale pipe testing takes a little bit more time and effort. But really, there were over 75 pipes that were analyzed. There were some done in a lab situation like you see on the left, where they were deflected and strained up to 20% deflection, obviously to accelerate the stress level in the pipe wall and accelerate the stress condition. Concurrently, there was a series of pipes that were actually studied in simulated load cells, actually buried in soils with stress plates and significant amounts of stress being placed on that actual soil loading and column itself, to give a even more representative sample set of a true buried condition with confining stress on the sidewalls of the pipe themselves too. So I'm going to talk primarily and show some of the data that was done with the field testing in the actual load cell itself, which is probably the most representative of stress levels in the field. Keep in mind, these pipes were deflected at a very high level, upwards of 20% deflection. And many of these were designed to fail in a fast fashion as well, with very poor stress crack resistance, specifically designed so that we can actually validate that the modeling being done can happen, because otherwise this testing would have been going on for many, many years, and there's budgets to everything. So the news from the second part of the testing that was really exciting was that the predictive modeling from the UCLS test and the last NCHRP reports really provided a very conservatively accurate range for when the first time to cracking is really witnessed and observed in the pipe wall itself. So you can see in some of the pipes where the predicted time to cracking would be between, let's say, pipe 6, 71 to 220 days. The actual time to first cracking that was measured and recorded was right around 185 days. And that really held true for just about every single pipe that was tested. There were some that were predicted to, see cracking well above and beyond the 2-year time frame, and really no cracking has been seen or witnessed up to that 2-year mark, and they stopped doing the testing at that point because it basically validated the model. So in essence, they really were excited about the fact that the lab testing that was done did a very excellent job at identifying contamination, and that it is very translatable from a predictive service life standpoint to actual field results and when we see cracking in a fully manufactured pipe. So in addition to those 2 steps of research, there's also some additional research that was done by Dr. Michael Plummer to verify if there's any other concerns from a fatigue standpoint with recycled contents in HDPE resins. This is a photo from the project site itself, but in essence, his PhD dissertation and the research work that he did with Villanova University was really geared around towards creating a highly trafficked, highly fatigued, loaded situation in a commuter rail application, and trying to identify if there were any serious differences in the way that the pipe received, the amount of strain it was seeing from dynamic loads, and if there was any indication of cracking due to fatiguing in the recycled versus a controlled segment and complete virgin resin. So this is a nice visual example of what kind of test setup they utilized. Basically, on the left would be a typical AASHTO M294 pipe manufactured with virgin materials. And on the right, you'd see actually an ASTM F2648 pipe, which has been, like I said, primarily utilized in just private and land drainage applications. The cover from the bottom of rail to the top of the pipe was 2 feet. As a funny side story and note, typically their standards don't allow any pipe to be within, I believe, 6 feet of the bottom of the rail. So when they showed up on site to install these pipes, there was actually an expectation that it was going to be much deeper. but because of circumstances on the project, they were able to install them with only 2 feet of cover, which really gave us a much higher quality data from a live loading standpoint and a dynamic loading standpoint to analyze and take a look at. So this is a nice look at some of the analysis that was done over, I believe, 3 to 4 years through various freeze-thaw cycles. The commuter rail itself is the Southeast Pennsylvania Transit Authority that partnered with Dr. Michael Plummer on this project. And that's obviously him looking at strain measurements and gauges that were put in the pipe themselves. This is a typical look at what kind of strains were seen in the pipe walls themselves, whether virgin or recycled. And really the nice thing about this diagram, it really shows you that the amount of strain that was seen from dynamic loadings was very comparable between the 2 manufactured pipes. And there was no cracking that was observed or witnessed in either pipe, whether recycled or virgin. So the responses to the loading were very comparable. This is in micro strain. And the actual long-term performance was, from a cracking standpoint, over that 3-year window, didn't show any visible signs of a crack starting or forming due to fatigue from the septic trains. On top of that live load real world application, Dr. Plummer did some additional research in the lab to really enhance and increase the amount of cycles that the plastics themselves are seeing. So they decided to punched out samples of the actual post-manufactured pipe, including, you can kind of see the valley and the corrugation meeting the liner there. And they placed the actual punched out samples from manufactured pipe from both recycled and virgin, and they tested in a lab condition where they are basically pulling on it with a significant amount more micro strain than you would typically see in a live loading application. If you noticed in the slide before, it was in the hundreds range, and the micro strains seen in these tests in the lab were in the thousands range, almost up to 10,000 in some of the peaks there and amplitudes there. So from a fatigue standpoint, you can see on the data here that the samples were tested up to 10 million cycles with no cracking observed, even when seeing a significant amount of post-consumer recycled resin in the pipe and in the samples themselves. The fact that there was no visible cracking and no recorded cracking even up to 10 million cycles it yields to the fact that recycled plastics are really showing no difference from virgin in terms of its response to fatigue. They're excellent materials at handling repeated live loadings, and they're excellent materials at handling that dynamic strain that's placed on them and rebounding and staying in the position that they're supposed to be. So the net of his research was that fatigue is not a concern and not a critical concern for recycled HDPE resins, any different than virgin resins themselves, which is a really great thing to see as well. So just to reiterate and to outline some of the changes in AASHTO and M294 that will be published here this fall, there's going to be no reduction in performance requirements whatsoever if you're utilizing recycled resins. It needs to have the same cell classification, has the same NCLS or notched constant ligament stress criteria. It has to have the same structural properties, the same pipe stiffness. None of the standard is changing from that standpoint. What is changing is really an addition of a significant amount more testing if a manufacturer chooses and decides to use recycled resins. If a manufacturer chooses to utilize recycled resins, they will obviously have to do the UCLS test, ASTM F3181 test that I showed from NCHRP 4-32. That must exceed a minimum calculated value to ensure a 100-year service life. There will be an additional test to test for antioxidants in the recycled blend, which is called the OIT test, of 20 minutes. That limit was really set there based on a lot of research from the gas pipe industry and others that have done extensive testing on what type of antioxidants and what volume of antioxidant packaging is required to prevent that chemical or oxidative failure. And in addition, there is an increase in a redundant contaminant test in the elongation and break test, which is basically where they take and they do this typically for typical tensile testing and ductile testing for even virgin resins. but they'll be taking those samples and it cannot break before exceeding 150% elongation in those wishbone samples. So from the research, no reduction in the performance requirements for that specification, but it does enable manufacturers, if they want to go through the rigorous testing that's put forth, to utilize recycled resins and incorporate that into the product itself too. In addition to the specifications, revisions, and changes, there's also a standard recommended practice that outlines a lot of what I've discussed about determining the service life of corrugated HDPE pipes manufactured with recycled resins. That will be published as well alongside the updated changes to ASHTO M294. One thing I do want to share as well is that from a quality standpoint, the amount of testing that's done currently on virgin resins will be significantly increased if you do decide to use recycled resins. The frequency at which we run the standard NCLS, carbon black, tensile strength testing, all of the testing that's done on virgin resin, when you use recycled resins, it will be exponentially increased, almost 30-fold into the amount of testing that we'll have to do on both pre-manufactured and post-manufactured product utilizing recycled materials. So from a quality standpoint, a lot of those details are still being worked out with NetPep, who is the national program that AASHTO utilizes for auditing and certifying plants for production. It's going to be a very extensive amount of testing that's required to be utilizing recycled materials too. So there's really no reduction in performance whatsoever by incorporating this, which is really the goal of the entire research study. Can we utilize this very large resource stream, be environmentally responsible, and frankly, use our resources better as a country towards something that still requires a rigorous service life and performance level? So if we can take that 6-month service life bottle and turn it into a 100-year service life drainage pipe, that really is adding some serious value to our infrastructure and to our resource management stream as a whole. I know I went a little bit quicker than expected on this, but I'm sure there's a handful of questions that I'd love to address and talk about as well. And I do have some other content that I thought about adding in here as well, but I wasn't quite sure how long this would go. So I will at least offer this back to Katie to start answering any kind of questions or data that folks would like to talk about as well.
Thank you very much. We do have a couple of questions, but for those of you who haven't submitted any yet, as a reminder, if you'd like to submit a question, please type it in the question box and then I will read it aloud to Bryan. The first question came in pretty close to the beginning of the presentation, and the question is, were you giving the net savings from recycling plastic, or are the costs of recycling the plastic not considered in those numbers?
So the recycling figures that I was giving was actually pulled out of a study out of Utah that was evaluating what the value of recycled plastics is. Their analysis incorporates actually the amount of energy and time and input into recycling it as well. Obviously, there is some cost associated with utilizing recycled resins, and we evaluate that very thoroughly. Obviously, from a manufacturing standpoint and a cost competitiveness standpoint, it needs to be attractive to buy resin that's from post-consumer sources, reprocess it, and then utilize it in a pipe product. It needs to be more cost effective than just buying virgin resin as is. So there is absolutely a incentive there if you can refine your processing portion to utilize it, and those figures that I was giving does incorporate the actual processing piece after the fact. I mean, from a processing standpoint, it's really the distribution, the logistical piece, and the fuel piece, and there is basically the electricity that it costs to run the plant, and there is some wastewater operations that we do on site, but obviously running that segment is important as well. So good question. I hope that was a sufficient answer as well.
All right, thank you. The next question is, when washing recycled plastics, what is used? Water, acid and water, chemicals and water, etc.?
There are no chemicals in the water. I think that's what they're asking. It is simply literally a settling chamber of water where the plastics float to the top. And if I went back to the slide to show the visual, there's basically blades that pick up and pull off the top of the wash bath and take the plastic off and take it into a conveyor system that starts to go further. And we run it through a couple cycles of a settling chamber basically to continue to do that process. But there's nothing special about the water itself. It's simply just a large settling chamber if you think about it that way. The one thing I guess I didn't mention from a quality perspective, I did mention other thermoplastics. In order to evaluate how well we're separating out the various thermoplastics, we do in our labs take the recycled resins in the flake and we put it in a mixture of alcohol and water. We reduce the density to 0.92, 0.925, which will basically create a very similar circumstance where you'll see the settling of the HDPE to the bottom of the jar itself, and you'll see a floating of lighter density plastics like polypropylene, which is the most difficult contaminant to remove, float to the top. And if we have a slew and a set of bales that fail that testing, we'll run it back and reprocess it again and usually pelletize it to remove a lot of that polypropylene as well. So excellent question. I hope that answered it, but nothing special about the water. It does need to be treated after typically. So.
Okay, the next question is, what fraction of consumer HDPE is reused?
What fraction of consumer HDPE is reused? I guess I would have to ask a clarifying question on that. If you're asking about the total volume available in the U.S. towards what gets reused, period, I wouldn't have the answer to that. I can tell you that we are the third largest recycler in the U.S., and we recycle about 420 million pounds of HDPE. We are the largest consumer of recycled plastics because we take that 420 million pounds and use it right back into a product. But there is a larger industry that utilizes recycled plastics for other applications as well. So I can't really speak to that as well. But, we have manufactured pipe with up to 80% post-consumer recycled resins and seen really high performance in that product too. One thing I didn't mention, when I talk about recycling, the one thing that it does incentivize and allow for us to use as a manufacturer is some very high quality HDPE resins too. So we don't just recycle post-consumer resins. We also recycle things like HDPE water main that's pulled off of a job site. That HDPE that's used for water main is usually really, really high quality stuff. And if we can get our hands on that and get it at a fairly decent price, because otherwise it would just be sitting in a landfill, we can really enhance a recycled blend, sometimes to outperform our virgin blends that are bought to meet the specifications. So recycling, although I think there's a perception out there that post-consumer plastics are terrible and they're not the highest quality and there's contamination. What allowing recycled content does provide is it provides us the opportunity as manufacturers to utilize a lot of those higher grade HDPEs too that would otherwise end up in a landfill. And the water main piece is one option. There's some others that I could probably share but are a little proprietary, so I can't. But that's a perfect example of where we can actually, I call it juice or basically really enhance the recycled resin with a lot of post-consumer, a little bit of very high quality HDPE and a little bit of virgin and antioxidant packaging to make a really high quality overall blend at the end of the day, which is really the key there in the entire discussion. So I don't know if I answered that question, but hopefully that was a little more educational on that process.
I have not received a follow-up from that person, so I would assume that you have.
Okay.
The next question is, what is the most difficult contaminant to extract from the plastics recycling process?
It is other thermoplastics. For all the reasons that we talked about, because they have very similar densities and the wash bath does the majority and the bulk of the work in terms of separating out contaminants, other thermoplastics are the most difficult. So, when you hear people, we do have some processes at the front end of our sorting, even where we actually can knock off some of the smaller caps of bottles. So if you look at a typical Tide bottle, the cap of that bottle, the blue cap, is polypropylene, and the body of the Tide bottle is actually high density polyethylene. So that first process of hand sorting is actually a really easy way for us to knock out some of those other thermoplastics, and you'd be amazed at how good the vibratory separators are at pulling out the caps and how good our hand sorters are at identifying what not to allow through. But even if that does happen, that's why we have the wash bath piece. That's why we do the quality at the end to check for that. And that's why we have additional processes like the pelletizing operation and the melting operation, where we can catch a lot of those other thermoplastics that don't melt at the same temperature in a screen. So it's something that we've gotten better and better at over the past decade or so at refining, and it's really a great thing to see. So.
All right, thank you. The next question: if China is not taking the recycled plastics, where do the extra recycled materials go? To a landfill?
That's an excellent question. Probably to a landfill. That would be the highest. That would be the highest likely scenario and outcome, is that it just ends up taking up more space in a landfill. So I don't quite know exactly what's come of that. I'm sure there's going to be more and more stories about that coming out going forward, but it certainly is a dynamic that a lot of folks, I guess, sort of expected. And that's a whole nother topic altogether. But regardless, it is a problem that is generated by that change in stance and relationship, and it's something we're going to have to address one way or the other. So.
Understandable. All right, the next question. Are there any special construction, storage, handling, or installation requirements for pipe with recycled plastics?
No. So the entire goal of that research, as outlined, was to assure that the performance of the pipe would not be affected whatsoever by allowing and utilizing recycled HDPEs. So no, there is no special circumstances above and beyond what is currently required for pipe manufactured for AASHTO M294. It's treated the exact same. So excellent question. Thank you.
Okay. The next question. When you recycle an oil bottle like that used in auto engines, what happens to the oil that sticks to the plastic? Is it washed off?
That's an excellent question. That is probably handled more at the actual distribution and recycling facilities that we buy the bales from. And if they do not provide us with bales of plastic that meet our standards, we reject them because we have certain quality standards that we're trying to meet at the end. And that feedback has actually improved a lot of our inputs and a lot of our inflow from those 100 or plus so distribution facilities and recycling facilities. So in terms of what happens to the oil itself, we do if there's any residual oil on the product as it goes through the process of sorting and then washing, when we do the drying piece and it comes out as a dry flake, we go back and test for moisture content and things like that, which is not testing for oils, but the end result in the flake that comes out has no residual fluids or liquids on it whatsoever. So that oil is likely going to be caught in and have to be treated in the wastewater treatment process after we have to cycle out new water in the wash bath, or it's that's basically it. We do some other mechanisms to remove moisture and liquids from the plastics after they're ground up and gone through the wash bath. It's not just the wash bath, but again, if I gave you the full suite and tour, it'd be even more impressive, the amount of time that's spent into creating that clean flake material at the output and drying it entirely from moisture and from any other liquids or fluids too.
All right, thank you. The next two questions are closely related. The first one is, does the extra testing impact the cost of the product? Overall, how does recycled HDPE pipe compare to virgin HDPE pipe regarding cost? And then the second one is, how does the cost of the pipe with recycled plastics compare to the pipe of virgin materials? So they're basically the same thing.
Gotcha. So the additional testing certainly adds cost, but for the most part, at least from our initial evaluation, from an individual business standpoint, is you will likely not see any difference in cost between the two. And there's really a couple of reasons for this, but one of them is going to be the amount of rigorous testing that's going to be required on manufacturers for making sure that it meets that quality level, which is obviously critical. I mean, we're willing to take on that bear of a task because the quality of the product means everything to us and does as it does to our end users and towards municipalities or DOTs or anybody that's looking to specify this, or engineers on projects for public applications. So the quality piece is really the most important thing. Long term, from a financial standpoint, I think you'll see that recycled resins will have a much more consistent cost profile. So in terms of protecting public agencies from construction inflation costs and from long-term accelerants in costs of materials, utilizing recycled plastics enables really the manufacturers and the end users a much more stable cost, which there are a lot of factors that can affect the cost of materials, whether it's, again, the foreign policy shifts that have happened in the cost to steel, or it's something that happens like a natural disaster or an event that hits a manufacturing facility of HDPE resins. There are a lot of things that can happen that can significantly affect that virgin source of material. The recycled piece will bring so much more stability to the end construction cost for end users and municipalities long term. So when we're looking at that ASCE report card, obviously we're not looking at tomorrow's project, what is this going to cost? It's really looking at that 20-year outlook and the available funding. And I think you'll see a very stable cost for the product, comparatively speaking, if it was only allowed to be used with virgin resins.
All right, thank you very much. There's just a point of information that somebody provided stating that NPR reported months ago that excess not going to China are actually going into warehouses or landfills if there is room. So did you have anything you wanted to add to that, or should I go to the last question?
No, that thank you for that feedback. If you saw on that slide, that picture and the link I put at the bottom was to that very same article that I believe is being referenced. So so thank you for pointing that out, and that's why I had that link down there, because that wasn't my picture and my data and information. That was coming from NPR as well. So thank you for the validation of that.
Awesome. And we do have one more question, so we'll go ahead and squeeze it in. Do you use the metals that are removed from the sorting process?
So we do actually. Excellent question. The bales, when they come in, are actually strapped with steel. So when we cut those, we actually recycle those and send those to a steel scrap plant. I'm not quite sure about other metals like aluminum or others that are pulled out in the wash bath process or underneath the conveyed magnets, basically. I'm not 100% sure if we do or what we do with them, but we are doing everything we can at that facility to do exactly that, to go work with a scrap processor. And if it makes sense for them to buy it and to take it and they can reutilize it, and there's a good business case for it, absolutely, there's no reason why we couldn't utilize that. I'm not quite sure how much refining we're doing of the wash bath waste. I think for the most part, we're simply trying to treat the water to be reused, or simply if it's obviously put into drainage, that we're not dumping wastewater into something. Historically, we had been hauling, at this facility in particular, hauling our wastewater to a local wastewater treatment facility, and it was being treated adequately there. So I don't see why there couldn't be an attempt to continue to utilize as much of that material as possible. And we have worked with, there are other things as well, like the paper labels on the bottles and things like that. We have, there's a lot of insulation and other things that can utilize some of those products as well in other applications too. So we do have the ability to really segregate and separate out every single component of that recycling piece. The most important to us is HDPE, but we work with other recyclers to take some of that additional waste and utilize that elsewhere too. So, excellent question.
Awesome, thank you very much. As a reminder to all of you that joined us today, a link to the handouts and quiz can be found in your confirmation email. And be sure to complete your quiz by next Wednesday to ensure timely delivery of your PDH certificates. I'd like to thank Bryan for his wonderful presentation today, and thank the rest of you for joining us, and we hope you have a wonderful weekend.
Thank you, Katie, and thank you, everybody.
Thanks, bye.